Welcome to Homebound Science. Today we're going to be talking about sound. Have you ever wondered why when you walk into some auditoriums the seats are nice and cushioned and other times they're hard? Why sometimes if you're making a sound in one space it resonates and you get a lot of reverberation happening and it sounds fantastic, and then sometimes you make the same sound in another space and it sounds not nearly so nice? It's all about sound absorption and reverberation. It's acoustics. It's science. So today we're going to do some very fundamental exercises in this just to get our feet wet. That's all we're really trying to do here. We'll dive more into it in future episodes because our goal is to make an instrument. And if we're going to make an instrument, we need to know how sound works. First, let's talk about sound absorption. Sound absorption is what happens when the sound waves that come out of our instruments, come out of our mouths, come out of anything that makes a sound, hit a soft object. They get absorbed into the object. For instance, this little Beethoven right here. Sound comes into him and gets absorbed. Doesn't bounce off. My little metal guy, not big enough for anything to actually happen, but sound waves come in and bounce off. They don't actually absorb into the metal. So when you walk into a theater and you see the cushions on the seats and it's nice and comfortable, it's not really actually there for your comfort. It's there because it approximates the sound absorption of a human being. Remember, most rehearsals don't happen in front of people. And so if you're sitting there trying to make sound and trying to figure out what your sound is going to sound like in an auditorium, you want it to be like there are people there, but not actually being people there. Otherwise, you walk into the auditorium on the performance night and it sounds completely different from everything you've practiced. The cushions in the seat act just like a human would. They absorb about the same as a human would, so that when the human sits down, the sound absorption of the room didn't change. The acoustics of the room didn't change. The sound the performer hears from the stage is the same sound they've heard this entire time of practicing. Now, there have been some composers, performers, who've actually wanted you not to be comfortable in an auditorium. The most famous of them, his name is Wagner. He's a German opera composer who would write these very long operas. And his preferred method for you to sit is hard wooden benches that are incredibly uncomfortable, so you could not fall asleep and had to pay attention to the music. Now, sometimes when we're talking about sound absorption, we want rooms where sounds are absorbed. Think my apartment that I'm in right now. I have a trombone that I can't really practice because my neighbors would hear it. And while I'm not a bad player, it's not nice to my neighbors to hear my trombone playing. Especially practicing doesn't usually sound good because you're working on stuff you don't get, and drills and exercises aren't the prettiest of music. So to make this more sound absorbent, what I would do is put cushions on the walls and ceiling, and probably underneath the floor, to absorb the sound. However, if I wanted a performance space, I'd want as much natural sound as possible. To make as much natural sound as possible, I would want the walls to really bounce the sound back. That's how you get a resonant sound. That's the sound waves bouncing back and forth before they eventually get absorbed. When you're thinking about a hall where you sound really, really good, often it's because the walls are incredibly hard, the floors are incredibly hard, the ceiling's pretty hard, usually made out of tile and cement, and so the sound carries a lot more. Smaller spaces tend to be more resonant than bigger spaces, although design can help with that, because again, there's less distance for the sound to travel. We don't want sound to have to travel a lot, because as it travels, the energy dissipates, and eventually the sound dies out. We call that the envelope of the sound. We'll get to that later on. When we're thinking about sound, a very easy way to look at absorption versus resonance is to look at a pillow versus a box. When I was doing a lot of work in this, I was using an Altoids tin as a really good resonator. But we're just going to start with a pillow. This is a pillow my grandmother made me, but grab any pillow. What I want you to do is put it over your mouth, not your nose, but over your mouth. And how much of the sound is taken away by doing that? You can hear some sound, but it's not resonating anymore. Sits there and dies. Now let's look at another type of object and see how it makes sound. Instead of the pillow, we're going to use a glass bottle. We'll use it later to figure out how woodwinds make sound, but today we're just going to look at the basic resonance. So the first thing we're going to do is we're going to tap it. Especially with our fingernails, see how it makes a bigger sound? That's with my fingers over here absorbing some of that sound. Now, if I talk into it, you can hear the sound coming back a little bit, the air. It may not come up on the mic, but you could do it, you could hear it if you were doing it by yourself. It also works with plastic bottles, works with a lot of different things. Again, I used an Altoid tin in undergrad. Basically what we're trying to do here is we're trying to see which objects absorb sound and which objects increase sound. That's the real job of a resonator, is to take the vibrations that sound is and make them bigger. It's what your speakers do. That's what the body of a guitar or a violin does. That's what this big body of the piano does as well. So what I want you to do is I want you to find a few different objects. I used a pillow and a glass bottle. You can use a pillow, you can use a glass bottle, you could use other things as well. I want you to find a few though. And I want you to compare how they carry sound. What kind of sound do they make? What kind of sound do they make when you add sound to them? Make a table, compare the results, figure out which objects are more resonant, which objects are less resonant. What do the objects that are more resonant have in common? What do the objects that are less resonant have in common? How could we use this information to help us when we eventually design our own instrument? Have fun and happy science.